So before starting today's lecture, so this is the last lecture, so I try to finish things. And maybe let me recall what I spoke about in the previous lectures. So in the first lecture, I explained something about the scattering. So then we consider some very simple model. So the content is summarized here. So we consider this kind of operator. So L0 is an operator which moves a function to the right. Okay. So it's a big, in some sense, it's a big operator, but actually it does not do much things. So just this is a transient. So things comes from left and go to the right. So we don't find anything very special. But we consider the situation that there is some interaction or something happened in the middle. So, and we suppose that this is some small operator, like a finite rank, or sometimes it is a compact operator, or maybe trace class. Okay, and in such a situation, we can compute, we can consider something called resonance as an eigenvalue of some reduced operators. And also, in some sense, in some case, we can compute the trace of such operator as a trace of K, right? Because L0 do not have trace. So it's natural to consider that this sum, that the sum of this, the trace of this sum is just a trace of this one. Okay. So this is the idea we have. And then I want to see that actually if you consider a transfer operator for Anosov diffeomorphism or some hyperbolic diffeomorphism, then we can find this structure. This is what I like to claim. And for this, I introduce some wave packet transform. Actually, wave packet transform is quite a general framework in functional analysis. It is not very popular because, as we saw yesterday, to set up wave packet and some argument is not easy. So, but the good point for this wave packet transform is that once we set up the language, then everything looks very clear and maybe quite geometric. So the first step of the construction of wave packet transform, so there are many ways of constructing this, but maybe one way is that first we fix some metric. And this decides the size of wave packet. This is a metric on the cotangent space. And then adapted to this wave packet, we construct, adapted to this metric, we construct some wave packet. And okay, I don't repeat the construction, but what I got is that we consider some family of functions parameterized by element of cotangent space. And if you consider in the space, so this, if you consider this function, then it concentrates around x. So here, rho is x and c, and it concentrates around c, x. And this size is basically given by the metric. And then, if you consider the Fourier transform of it, maybe this is f phi rho, then the size is again given by this metric. So for this, actually, we have to adapt, consider the metric which is which pays respect for uncertainty principle, and in some abstract language, actually the metric have to be compatible with symplectic, standard simplex structure on the cotangent bundle. Okay, so there are a few very weak or some obvious restriction for the choice of metric, but for each such a metric, we can construct a wave packet like that, like this. But maybe we do not go into such a general argument. We just consider some fixed metric, and then we constructed the wave packet. Okay, and then we consider the wave packet transform. This is basically the decomposition into the wave packet. Okay, and phi star is a reconstruction. So first, if you are given function u, then we get the function on b on tangent bundle. So we consider that the function u as an superposition of many wave packet, and the weight is given by this function. And then again, reconstruction is that if you have a function here, then you reconstruct the function by superposing those wave packets. Okay. And what we found is that okay, this works well. So and then Lhat, we consider this operator Lhat. This is basically from the family of wave packet. We reconstruct the function, then push forward by L, and then decompose into the wave packet. And this is written in this form, and actually the kernel is smooth. So it's a very simple operator, and the kernel is given by this. And so this is quite computable. And last lecture, I gave this formula or estimate. So let me begin with why this is true. So I don't prove this because it involves some computation using integration part. It is not difficult, but it is not suitable for doing in Blackboard, at least for me. So, but intuition is simple. So if you this is a product of two. So basically L2 norm of this L2 in the product, right? And so first let us consider phi rho. This is a function. This is centered at x. So rho is let us consider rho dash. So rho dash is x dash c dash. So concentrated right around the x. And if you look at closely, then it oscillates very fast. And okay, so if c dash is large, then it oscillates very fast. And maybe the oscillation is c. Frequency is c dash. Then we push forward by L. Okay. Then we get some other wave packet. Okay. Of course, you can imagine that the image will concentrate around, say, t, so the transfer to tx dash. And how about the frequency? So frequency, if you approximate t by its derivative, so linearization, then actually it is simple to see that this should be -1 rho c dash. So this is basically what I write this. This is dt -1 star rho dash. Okay, and then we take product with this. So this is another wave packet which is at x. Okay, rho is xc, right? And because we take a complex conjugate, the frequency is minus. So frequency is c minus c, right? So we take this product, then okay, the frequency of product is basically the summation of these two. Okay, this implies that okay, this is appeared here in the C component is that one. So, for example, if x and tx dash is far away with respect to this distance, then okay, there's no interaction. Basically, they are separated. So we see that this is small. And even if they are close to each other in the position, but if this frequency vector is far away, then if you consider the Fourier transform, then in after Fourier transform, they are separated, right? So again, this is small. Of course, if you like to have this high power, maybe we have to look things more carefully. But this is the reason why we have this decay. Okay. Now let us look at the implication of this. Yeah?
So as you explained already yesterday, if the dynamics is C infinity and the weight is C infinity, which is your assumption for this course,
yeah,
then you can take n as big as
yes.
But if the dynamics is only CR,
yeah,
can you do something in any dimension, or you need R to be depending on the dimension with this method?
With this method, no, not much. I don't think we can proceed very much. Because R is...
Does the limiting differentiability depend on the dimension?
Yeah. So, I mean that if you have some sufficiently large differentiability, we can proceed with this.
Depending on dimension.
Yeah, depending on dimension, yes. But otherwise, yeah. Especially if the derivative have discontinuity or something, then it's very difficult, I think. Yeah. Okay, so up to this point, actually, we don't use any hyperbolicity. Just this is applicable for any setting, any diffeomorphism or time t maple flow. So what I'm doing with Frederick recently is to apply this method to the flows, axiom A or Anosov flows. But okay, let me restrict myself to the Anosov diffeomorphism. And so suppose that T is hyperbolic. Okay. And I want to emphasize that, okay, so this implies that this gives a relation between the operator Lhat and the action of transfer operator, action of T on the cotangent bundle, right? So let us see that in a hyperbolic setting. So if you have T is an, yeah?
Where is this? The hyperbolic structure is not used here.
Yeah, for the moment.
Very general.
Yeah,
Okay.
yeah. So now let me explain how the hyperbolicity come in. It gives a structure. So, okay, so for T, actually we have, okay, in this case, this maybe you may not remember, but maybe I did mistakes in the order of lecture. So actually, so here I like to remember that what I defined in the beginning of last lecture. So, okay, so we consider some hyperbolic mapping. Hyperbolic, it implies that in some direction it is expanding and contracting. So, okay, maybe you all can imagine this. Okay, and so orbit goes this way. Okay, this is T, and how the action of T on the cotangent bundle look like? So in position, things move like this, but in cotangent space, okay, let us ignore the x direction. So we only consider xi. So here, this is basically xi u. So this is unstable direction. This is stable direction. So CS. So now things goes in a different direction. So we have some expansion in this direction. So action of dt minus 1 star look like, so basically it's in contraction in this direction and expansion in this vertical direction. This is the action on the cotangent space. Okay. And what this lemma tells is that suppose that you have some point here, it representing one wave packet. Okay. Then after that, basically it is moved by this operator, and maybe in the x direction this operator, and the image. Okay, suppose that we have Dirac delta here, then it's moved here, but you have some diffusion. And what lemma tells is that outside of this, actually, there's almost nothing. Yes. Or more precisely, with respect to the distance, or that with respect given by that metric, if we think point far away from this image, then the image of this Dirac measure will decay very fast. So the operator Lhat looks like this. So this is a transfer operator given by this action on the cotangent space, right? So Lhat is an operator acting on the functions on T star R D, right? And this is, okay, this is not very precise, but some transfer operator associated to this T dt minus 1 star plus some diffusion. Diffusion, or I don't know, how to. And diffusion is controlled by that metric. So some if you look at that scale of this metric, then it is unit size. Okay, this is the picture we have. Okay.
To make this linearization precise, you use integration by parts or something like that. I'm not sure I understand.
Sorry, linearization?
So associated to the derivative, you mean it's a linear part. Is that what you mean?
Yeah. In the each of cotangent space, yes. But of course, actually, things are happening in 2D dimensional space. So I cannot write it. So maybe I write it in separate ways. So, but of course, this part of the picture is not very precise. So actually, it moves to here, but in different point.
But when you wrote here, there is a precise statement which corresponds to
This one? This statement? Precise statement for this? Oh, okay. Yeah. This is not a precise statement. Just imagine this.
But are you saying that's essentially the content of what's up here?
Yeah, in lemma. Yeah.
The lemma.
Yeah.
Okay.
So it doesn't say it concentrates, but what it says that outside of this neighborhood, then you don't find any big thing. Yes. Now, I think at this moment things are rather clear. So if you consider the function on this space, then something comes from the EU direction and goes out after a long time. It goes to the CS direction. This motion, and this corresponds to L0. And of course, in the neighborhood of origin in the cotangent bundle, it implies that low frequency. And so in low frequency level, we have something others. This is given by dynamics.
Wait, what corresponds to L0? Sorry.
L0 is just a translation.
To the linear map?
Sorry?
No, L0 is just a translation.
Yeah, just translation, and we consider some perturbation of this.
Okay.
And basically,
The K
yeah.
is the perturbation?
Yeah, perturbation. So,
What's your compact finite, right?
yeah. So I think we can imagine that this is very close to what we are doing. So we are coming from farther place and they get together here and do some interaction and then go away. So and then to measure what we are doing, maybe we have to look at something that like this and then maybe remove the effect of L0. Then this is what we do in this conference. So. Sorry, but anyway, so picture here corresponds to this moment. So if you consider this motion of function, this is just a transient. So it comes from this direction, maybe very high frequency, and then by the effect of hyperbolic dynamics, it becomes some lower, becomes. By expansion, it becomes some low frequency part, and then after a long time, then by the contraction in here, we get again the high frequency. We go into high frequency, and then we would like to see what happens in between. Okay, so we like to consider in this parallel way, but actually there's a few differences. So first, it is actually difficult to fix precise incoming and outgoing subspaces. It is difficult to find it. So yeah, morally, we can take consider the following. So this, and maybe here, the function supported here is incoming state, and thing supported here is outgoing state. Yes, but actually we only have that kind of estimate. So that some of the property that I mentioned for outcoming and outgoing and incoming subspace does not hold exactly. But we have that structure in mind. Now, okay. So, okay, resonances in Anosov different waves. So first, I want to set up function, but I call it weight function. But it may be better to call it Lyapunov function. So because there is some transient behavior here, so we expect that we can have some Lyapunov function. Of course, on the outside of some neighborhood of the origin. So we consider some smooth function, W. This is from T star RD to R plus. And we require two properties. So this first one is that this is a Lyapunov function for the flow induced by this action on the cotangent bundle. So W, but in some exponential sense, so or multiplicative sense, -1 rho. If you move a point rho by this, then this is okay. No, this is okay, -1 rho if C. Maybe this is not exactly equal to the constant lambda in the definition of T, but maybe it's a bit small. But okay, let us don't care about this. Okay, and so this is one thing, and the other thing is that this is necessary for some estimate, and this is called slowly varying property. It basically implies that in logarithmic sense, this function does not change very much in the scale of the metric. So there's some n and some delta and some c such that okay, if you consider this rate, double row dash, double row. No, maybe not. Is smaller than 1 plus c and c to the minus delta, and the distance between row n. So if you look at the scale with respect to this distance, actually the difference is not too large. Of course, if it is n may be, say, large number, so it can be large, but anyway in the polynomial order, and if they are close to each other, then this is almost 1, and if you think, sorry, maybe for any row in xc and row dash in x dash c dash. So if you go high frequency, actually, if you look for the function w, then it is almost constant if you consider things in the finite distance in this metric. And the construction of such function is rather easy. So, and there are many ways. So I don't do it, but maybe let me convince you that this is rather easy, because okay, there is some unstable cone and stable cone. Okay, and in this cone, maybe here we set that w is c to the, sorry, okay, this is proportional to c. Then if you are in this cone and coming to, okay, the action is like this. So if you consider this function, then you will get this decay. And also if you set here w is c to -1, then again, so in this case, here we have expansion in this direction, so you will get, again, this estimate. And clearly this satisfies this condition, and so we interpolate in between. And this is not too difficult, so we just interpolate. Yes, parameter what? Lambda or R. Yeah, we consider, okay, as a weight function, WR, actually, we consider the power of this function. Yes.
Psi to the power
Yeah.
R, psi to the power.
Yeah, yes. But for the moment, I just like to use this as an Lyapunov function. So if you consider the value of, compare the image value of W at a point and its image, then there is some definite relation like that, like one.
Xi prime does not come in the
Xi prime. Where? In the last one. So Xi dash is a part of rho dash. So. Yeah, I understand that there's something subtle because maybe actually we have to. Yeah, actually I skipped one or two things. So the metric, this metric, have few properties, and one important property is called slowly varying or temperate property. And this actually appears in the book of Hellmander. And for example, in this case, for instance here, actually what we have is that this rho dash rho is bigger than C to the rho minus rho dash and rho dash or something like this. So, or n. So, in some sense, and to get this, actually, we have to set that alpha is in between 1 and 1/2.
Just a general comment. If
Yeah.
we bog down Masato too much in details, he's not going to finish. So.
Oh yeah, okay. Yeah. But yeah. Maybe I'm skipping this. But so let me say that. So I'm, as I said, I'm working on this for flows, and we have preprint on the archive, and here we discuss it in very detail. How many minutes do I have?
16, 17.
Okay, maybe that is enough. So. So one, okay, it's 3.2. So at the composition of Lhat. For now on, we only consider that operator Lhat, and we forget about L, because every spectral property is same as of L and Lhat is almost the same. So the difference is just a multiplicity of the spectrum 0. So now we just set that lambda is rho dash in T star or D, 2, and rho dash is, okay, some lambda tilde 1 is 1 and double rho. Say we take lambda 0 like this. And sorry, yes. And also, I want to assume that C dash greater than C and C greater than C. Maybe depend on T. So, and then with this set, using this, we decompose this operator. So L hat is written as follows. So K, this is a kernel, and then L hat, rho dash, rho dash, okay, U, sorry. L hat U rho is the U rho dash D rho dash. And so decompose it L0 hat plus K0 hat. And L0 hat is just a restriction of this kernel to this set. So maybe we can write it in this form. K, maybe this is not good. So this is 1 lambda rho dash, then K L hat rho dash U rho dash D rho dash. And K0 hat is just a rest. So we consider complement here. And I like to take this decomposition as an realization of that decomposition. Or, okay. Then, okay, well, I like to state the theorem that corresponds to theorem A. So, for function space, actually what we consider is this space. This is actually T star R and W is U, now V in L2 local T star R and W U V. L2 is okay. Is finite. Yes, sorry, thank you. RD and this is RD. Then theorem, let me write that theorem A dash. So L hat, L0 hat, K hat, L2 W is bounded. And first, the operator norm L0 hat is it's up to the minus R and determinant of dt and the 1/2. So it have the part L0 have small norm because of the weight. So this is completely the same as the case of that matrix model. And then second, K is L2W is compact. or actually in trace class in very strong sense. So this is, I mean, maybe if you don't know about functional analysis, maybe you can take it that it is very close to the finite dimensional operator or finite rank operator. So close to the finite rank operator in the operator norm implies compact. And if you consider things in the trace class norm, then this is a trace class operator. And we have this. And
So I'm not sure I have to ask you a question.
yeah, no, it's okay.
C0 does not depend on T, it depends only on G. That's the point, right?
C0, yeah, yes. This does not depend on R, yes.
And it does not depend on T.
Yeah, okay, yes. And sorry, I forgot very important thing. So I want to here R. So R is, okay, sorry. I did very wrong. So yeah, so this is the power of W and R. And okay, yeah.
Yeah, so this is a question I didn't dare to ask, but my question is not that. My question is C0. The
C-
constant C0 in the first
Yeah,
part,
this question.
it does not depend on big T on the dynamics, right? It only depends on the weight G.
Wait,
Because otherwise I don't understand why this determinant appears. Is it part-
yeah. You're right. Yeah.
Okay.
Yeah. Yes.
Or no, it depends on the weight, the pressure. So I'm not-
Yeah. If you like this, but
All right, I have actually a question,
yes.
but this is less about a detail. So lambda, so that I don't have to figure it out in my head, is that, should we think about that as the, just the transient part, the outgoing transient part, the ingoing transient part? What roughly is lambda?
So this is basically transient part.
This is the transient.
Yeah.
Okay.
Yes, incoming and outgoing.
Okay.
Yes.
So can you explain the WR?
WR is just the power, R power of W. The W is a function that we take
I tried
there.
to get him put it on the first diagram. He didn't want to. Now he's there.
It's easier to put it in.
It's okay. Yes.
Then I have to put W.
Okay, so now let me explain about this. So there's only one subtle point in the proof. So maybe I like to concentrate on this. So first, let us forget about the weight. Then, what we have for the L2, just the L2 norm. Okay. Then this is phi. Okay, maybe this is phi and L2 norm, and then phi star in L2 norm. And actually this is a 1. So we can forget about this, or at least it is bounded by some absolute constant. So we have L2, and then, oh, yes, I now realize what Vivian told me. So, okay. Sorry, so for simplicity, just forget about, no. Yeah, you're right. So maybe it's better not to, or, yeah. Okay, okay, this is not important. So, okay, let's say this is G and T. Sorry, this is. And then it's clear that this is bounded by some constant G and T. Okay, this is quite clear. And then we start to consider about the weight. But let us consider the part where frequency is high, because the set, if you consider the, okay, we are going to prove the claim 1. Then, of course, in the definition of set, we suppose that the frequency is high. Okay. And so we consider that kind of wave packet and how it moves. But now the second property of W implies that actually if you look at the scale of wave packet, actually W is almost constant. So actually what we have is that we have some constant multiplication here, right? And compared with norm multiplied by constant given by W rho. Okay, so actually then the first property proved that the first claim hold, right? So the point is that so the function W is quite flat in high frequency. So we may think that if you consider things in the size of a wave packet, actually it is constant. So what happens locally is that this plus some multiplication by some constant. And if you think about a little bit carefully, then we will see that the condition W2 gives the estimate 1. This is one thing. And the other thing is that, okay, kernel of K, so K hat, rho dash, this is basically equal to L rho dash, and 1 lambda rho dash, and complement, right? But by the definition of W, we see that if we consider this pair, so dt minus 1 star rho dash and rho dash. Okay, it is contained in lambda. And actually, it is far from the boundary. So actually, this implies that if you are in the complement, actually this is very small. So this is maybe if you take this, then this, I think we can say that maybe C to the maybe minimum of C minus C, maximum, and some arbitrary large n, minus n arbitrary large. It implies that basically this operator k hat concerns only the low frequency part. If you go consider things in the high frequency, actually there's almost nothing. So this concerns only low frequency, and it gives a reason to, and of course the space is in some sense, compact. So this gives the compactness of the operator. Okay. Then, okay, the last word is that, and of course, if you apply this to the decomposition of Anosov dependent morphs into the transfer operator of this form, then you can get theorem A. And finally, let me just point out that for trace, because it is sometimes strange that we can compute the trace of the operator Lhat. But actually, one simple idea for to define the trace for operator is like this. So this is called flat trace. So this is Lhat. We like to compute it. But one idea is that, okay, we have that expression. Maybe, yeah, using the integral kernel. So K, Lhat, and so we just consider in the same way as in first grade linear algebra, we just take the sum of the element in the diagonal, so D row. Okay. But of course, we can decompose it into two parts, Lhat and Lhat 0, row, D row, plus K hat, row, D row, this way. But if you examine the kernel, this kernel, actually this is 0. Okay. Because W is a Lyapunov function, and okay. Okay, so we have this part is 0, and on the other hand, okay, this is actually okay, we can write it as a flat trace of the operator K hat. Okay, this is just a definition. But since this is a compact or trace class operator, so it is known that, so once this is a legal object, so this is quite close to the finite rank, so we can define that trace of the operator K hat in a legal sense. And one way of computing this is just a flat trace. And once we have this, actually we can compute this in different ways. For example, using the eigenvalues. And with this, we can get to theorem B. And also, if you compute this is not difficult, but if you compute this, then you get this. T y minus y and I minus dt minus 1 and dy. Maybe if you are interested, maybe you can do this by yourself.
Little g is capital G? Or is it long?
Yeah, if you, no, maybe I consider this T and G. If you remember. Okay, I finish here.
We have time for one quick question.
So I complained, and then you remove the square root of the Jacobian.
Sorry.
In theorem A prime, the first bound, there was square root of the Jacobian, yes?
Yeah.
And I complained and you removed it.
Okay.
But now I would like to know, how does it appear? Does it appear in the story somewhere?
Yeah,
part of
because if you estimate this, so this is just for L2 norm, right? So this is actually, we can bound it more precisely as a maybe supremum of G, and then determinant of dt and 1/2, and maybe infinity, right? For if you consider the action of L on L2 space, then you get this bound.
Okay.
Yes?
But
okay.
then which operator will have spectral radius 1? For which G do you have spectral radius 1? Or this is just a bad bound? Is that what you're saying? Or it's not a bound for the spectral radius, it's a bound for the norm.
Bounded, so this is operator norm, have this operator norm 1. This is isometric embedding.
So let me ask the question differently. If I take G equals 1 over the Jacobian,
okay,
then the spectral radius of the operator on this Hilbert space is going to be 1? No. Spectral radius is different. So it's not the usual spectral radius.
Spectral different. Spectral is.
No, just answer my question. Is it equal to 1 for 1 over the Jacobian, the spectral radius? Yes or
spectral
no?
radius of this. Or
No. The transfer
that
operator on the Banach, on the Hilbert space that you define in theorem A.
So the spectral radius of this operator, you mean? Or
I guess this is a notation for it, yes. The operator which appeared in the main theorem A from the first lecture. Okay, maybe we should discuss later.
Yeah,
okay,
but let me just comment that this operator is. Yes. We are discussing here about in high frequency, so it does not capture that principal eigenvalue.
Okay, so this computation does not tell us anything about the eigenvalue, this computation.
It
just tells us something about the essential spectral radius.
Yeah, to estimate this, to get this one. Yes.
Thank you.
So actually there is one more question.
Yeah.
The peanut gallery, which is in your very beginning lectures, you talked about the ingoing space and the outgoing space, and you took a quotient.
Yeah.
Do those appear here?
No, it's difficult. Unfortunately. So basically there's some structure like this, but what appears is that it's very difficult to take that incoming or outgoing space exactly. This is at least difficult for me. I don't know how to do it.
So it's an analogy.
Yeah.
Okay.
So I think it's a very nice conclusion of the set of lectures. It is difficult. And okay, thank you again, Masato, for